Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of infinite temperature with no size, called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of -36 seconds and 10 to the power of -32 seconds, space expanded exponentially, growing much larger in size. After this period, space continued to expand but at a much slower rate, and eventually we see the universe that we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. But for a few physicists, the premier theory doesn't paint an accurate picture of the evolution of our universe. Rather, they say that the universe existed before that point, stretching forever into the past as well as the future. While the universe is expanding today, it was retracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang but a bounce, a moment when a shrinking universe reversed course and began to grow. According to their theory, the universe could bounce again. Today's expansion could be followed by a collapse in the far future, followed by another bounce. Some physicists have suggested this bouncing could be infinite. This, of course, is counter to the way most cosmologists see it, where everything started with the Big Bang. But what is noteworthy here is this is not the only theory that dares to challenge the pinnacle theory of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing, adding a bit of tension. The James Webb Telescope has made a bunch of unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. All of these raise a question. If the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce or something else entirely? Join us as we dig deep into one of the thorniest issues in physics, the idea that the universe had a beginning or a day without a yesterday. As it was originally known, goes all the way back to George Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that described our early universe. Although many laypersons and even a minority of professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is out of date. The Big Bang now is not the birth of time and space we know that today. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff instead. Our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what occurred at the end of inflation. During inflation, the universe was completely empty. There were no particles, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new small-scale fluctuations are created atop them. This superposition of fluctuations of small scales atop intermediate scales atop large scales atop superhorizon scales is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on, but inflation will come to an end randomly and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happened at the start of a Big Bang before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a humanized hamster ball but perhaps much larger, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of 33 seconds or so, a brief amount of time but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise from just a few degrees above absolute zero to perhaps 20 Kelvin or so over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. It doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly. But when inflation ends and the universe reheats and the hot Big Bang starts, more distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees their expansion rate drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again and again and again. The process is relentless. But once the Big Bang begins, all of that changes as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region within spacetime, dominating its volume. These regions where hot Big Bangs occur will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view in the standard inflationary picture. Because of this expansion rate change, there's virtually no chance that any two universes where separate hot Big Bangs occur will ever collapse or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end. For us, the energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. But that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early time. The first one we've ever accessed comes from 380,000 years later after they've undergone countless interactions. Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem it has sometimes been called a crisis for cosmology. Third, the 2 hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense since we believe that the universe should have started out uniform on average. And lastly, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby celestial stars. Taken together, these anomalies mean we are missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology. Loop quantum cosmology, LQC, proposes a fundamental shift from the classical understanding of cosmology, particularly concerning the origin and evolution of the universe. At the heart of LQC lies the concept of quantum geometry, which suggests that spacetime itself has a discrete, granular structure at extremely small scales, on the order of the Planck length, about 10 to the power of -35 meters. This granularity prevents the existence of singularities such as the infinitely dense point hypothesized in the standard Big Bang theory. Instead of a singularity, LQC posits a bounce where the universe undergoes a phase of contraction before bouncing back and beginning to expand again. The idea of a bounce addresses some of the conceptual issues in cosmology, including the origin of the universe and the nature of time itself. According to LQC, time can be traced back beyond the bounds, suggesting that the universe may have existed in some form before our current expanding phase. This concept challenges the notion of a singular beginning and opens up possibilities for a cyclic universe model where contraction and expansion cycles could repeat indefinitely. One of the key features of LQC is its ability to predict observable phenomena that deviate from standard cosmological predictions. For instance, LQC provides insights into the behavior of the early universe that may explain anomalies in the cosmic microwave background, CMB, radiation, such as unexpected temperature fluctuations or asymmetries. These predictions offer testable hypotheses that could potentially reconcile discrepancies between theoretical models and observational data, providing a new framework for understanding the universe's origin and evolution. In addition to its implications for cosmology, LQC also intersects with quantum gravity, a theoretical framework seeking to unify general relativity and quantum mechanics. Unlike classical general relativity, which breaks down at the singularity, LQC introduces quantum corrections that smooth out the fabric of spacetime at extreme conditions. This quantum smoothing not only resolves mathematical infinities, but also suggests a fundamentally different narrative of cosmic history, where the universe emerges from a quantum regime rather than a classical singularity. Moreover, LQC incorporates insights from loop quantum gravity, LQG, which posits that spacetime is composed of discrete loops or networks, akin to a fabric woven from quantum threads. These loops interact with each other, defining the geometry of spacetime on a microscopic scale. By applying LQG principles to cosmology, LQC bridges the gap between quantum theory and cosmological observations, offering a more comprehensive picture of the universe's dynamics from its earliest moments to its current expansion. The theoretical framework of LQC continues to evolve with ongoing research and computational simulations that explore its implications for cosmic evolution. Scientists are actively investigating how LQC can account for the formation of structures in the universe, such as galaxies and clusters, and whether it can provide new insights into phenomena like dark matter and dark energy. In conclusion, while the Big Bang theory is the prevailing model for the universe's origin, alternative theories like loop quantum cosmology challenge conventional wisdom and offer new avenues for exploration. By integrating quantum principles with cosmological phenomena, LQC provides a fresh perspective on cosmic history and the fundamental nature of spacetime. Future observations and experiments, including advancements in astrophysical instrumentation and theoretical developments in quantum gravity, will continue to shape our understanding of the universe's origins and its ultimate fate. Most of us are familiar with the standard narrative of how the universe began. According to this narrative, the universe started from an infinitely dense point known as a singularity. This singularity had infinite temperature and zero size, and it exploded in an event called the Big Bang. This explosion marked the beginning of our universe, creating all the space, energy, and matter that we observe today. Between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the Big Bang, the universe underwent a phase of rapid exponential expansion known as cosmic inflation. During this inflationary period, the universe grew from an incredibly tiny size to a size much larger than what we observe today. This period of rapid expansion smoothed out the universe's structure, making it appear very uniform on large scales. After inflation, the universe continued to expand, but at a much slower rate compared to the initial inflationary period. Over billions of years, galaxies, stars, and other cosmic structures formed due to gravitational interactions and the clumping of matter. The Big Bang theory, particularly the inflationary Big Bang model, is widely accepted among cosmologists as it provides a comprehensive explanation for the origin and early evolution of the universe. However, this theory is not without its challenges and alternative interpretations. Some physicists propose alternative theories to the Big Bang theory. For example, instead of a singular beginning from a point-like singularity, some suggest that the universe may have existed in some form before the Big Bang. This idea challenges the notion of a singular beginning and suggests that the universe could have experienced cycles of contraction and expansion, known as a cyclic universe model. Renowned physicist Brian Cox and others have also raised questions about the Big Bang theory, arguing that the idea of something emerging from nothing, as suggested by the singularity, is problematic. This viewpoint adds a layer of complexity to our understanding of the universe's origins and evolution. Recent discoveries and observations, such as those made by the James Webb Space Telescope, have also prompted new questions about the Big Bang theory. Unexpected findings in cosmological data, such as anomalies in the cosmic microwave background radiation and discrepancies in the measurement of the Hubble constant, challenge our current understanding of the early universe. In response to these challenges, theories like loop quantum cosmology, LQC, have emerged. LQC incorporates principles from quantum mechanics and loop quantum gravity to propose a different narrative of cosmic history. In LQC, the universe's evolution is described as a series of cycles where the universe contracts to a certain point and then bounces back in a new expansion phase. This cyclical model avoids the singularity problem by replacing it with a bounce scenario, where the universe undergoes phases of contraction and expansion indefinitely. One of the key features of LQC is its ability to address some of the inconsistencies and anomalies observed in the early universe. For instance, LQC provides insights into the behavior of the cosmic microwave background radiation, explaining possible anomalies such as unexpected temperature fluctuations or asymmetries. Moreover, LQC offers a framework that integrates quantum corrections into the fabric of spacetime, smoothing out mathematical infinities that arise in classical cosmological models. This quantum smoothing suggests that spacetime itself has a discrete, granular structure at extremely small scales, known as the Planck scale. This granularity prevents the existence of singularities and provides a new perspective on the nature of spacetime at its most fundamental level. While the Big Bang theory remains the dominant model for the universe's origin, alternative theories like LQC continue to push the boundaries of our understanding. These theories offer new avenues for exploration and may provide insights into phenomena such as dark matter, dark energy, and the formation of cosmic structures. In conclusion, the debate over the universe's beginning is far from settled. The Big Bang theory has been incredibly successful in explaining many aspects of cosmic evolution, but it faces challenges and alternative interpretations. Whether the universe had a singular beginning or has existed through cycles of contraction and expansion is a question that continues to intrigue physicists and cosmologists alike. Future observations and theoretical developments will continue to shape our understanding of the universe's origins and its ultimate fate.